Let's take a look at paging. So in the book, you want to read a couple of chapters. This part is about introduction to paging. It's over here. And next up, we look at translation look-aside buffers. So remember, the problem is translating virtual addresses. Every address that you generate in a process is treated as a virtual address by the operating system, and it has to translate each one of these addresses to a physical or DRAM address. We looked at the base and bounds MMU approach, and that generalized to segmentation. And we had hardware, simple hardware, so things like a couple of registers and an adder circuit was pretty much all we needed to use this base plus bounds and then the generalization to segmentation. The operating system has to track these changes at certain times, but it was pretty much doable. However, there were problems with segmentation. It was not so flexible in that if you had an allocated chunk and this was used for the heap and you needed more memory from the heap, you might get boxed in. You might not be able to um, might not have space to allocate more memory because there's something else and you can't move that until something else is moved and so on. It'd be a pretty complicated problem. Also, what happens if we swap a segment out to disk because we needed the space? That itself is not a problem, but then bringing it back in, it's questionable as to whether you would even have space to bring it in. They're all different sizes. What if you happen to have if you swap out a especially large segment? But the main problem, the really big problem, is external fragmentation. Problem there is that you allocate a whole bunch of chunks, and then pretty soon what you'll end up with a lot of small areas of memory that are not in use but mostly allocated. That it's a problem by itself, but then the thing is that when you realize you could take each one of those little small segments that are not in use, coalesce them together and give you a nice big piece, that's memory that you could be using, but you can't because it's the actual pieces of available memory or not in use memory is all over the place in teeny tiny pieces, and so it's not usable. So that's a really big problem. The solution to all of this turns out to be paging. So the basic idea is take your physical memory, divide it all up into fixed size chunks called page frames. And then you do a similar thing on the logical side of memory or virtual address, virtual memory. Your process address space is split into pages. So it looks like I'm talking about the same thing. It sort of is, but it's not really. Frames, that refers to physical memory. Pages refer to virtual memory or logical memory. We'll use the term logical memory for now. Okay, so on the virtual memory side, we're going to have pages, and then the OS has to translate every memory access in a page into the correct physical address, or you have to find the page frame. Okay, so be very careful about these terms. Page frame refers to physical memory. Page by itself refers to logical memory. So this is the problem that we're going to solve, and we'll see that we'll need some help from the memory management unit of the CPU and other CPU hardware. Okay, so here's the crux of the problem. We'll use pages and page frames to avoid the problems of segmentation. So how do we do this? And what techniques can we use and to minimize the time required to do this and also the overhead in space that we might need to manage all of this? It turns out that we do have to pay a price in memory, that we'll need to keep some bookkeeping around for the operating system that uses memory, that uses space, and also it's not exactly fast. It's a little bit slower, but it turns out to be the best thing that we have. So there will be some time penalty and some space a penalty or space overhead, but we're going to try to minimize that. It turns out to work pretty well. Okay, so let's take a look at frames first. Physical memory, we divide it up into fixed size chunks called frames, page frames. Okay, so look on this side. We have a nice, small, manageable example from the book. It's only 128 bytes of physical memory, which is pretty small. It's not enough to do anything, but this is just an example. So we divide up the 128 bytes into 8 page frames. So physical memory divided up into 8 page frames. And each one of these frames is going to be 16 bytes. So 0 through 15, 16 to 31, 32 to 47, and so on. Okay, so you might ask the question, how many address bits do we need to address each byte? So it turns out there's a total of 128 bytes. There's 128 locations. Let's say they are each thing that we address is a byte. That'll make it simple. And so it's whatever 2 to the power is that will give us 128. Turns out to be 7. So there's 7 bits that we need to address these 128 bytes. So we might ask also, how many bits do we need to refer to each page? Well, it turns out if you're talking page frames, then we know the answer. It's 3 bits because there's 8 page frames. You need 3 bits to be able to address 8 things. So, however, if you say page, that means you're referring to virtual memory. So let's take a look at virtual memory first. So pages are the chunks that we divide logical memory into. So virtual memory or logical memory is divided up. In this case, we say that we use 4 pages. And so if we just had 4 pages in virtual memory, we only need 2 bits to figure out which page we're talking to. So 2 bits for pages. And so 2 bits for pages, and then each one is 4 bits for accessing inside a page. And so the total of that will be 6. So how many address bits do we need to address each byte of this process address space or virtual memory? That would be 64 bytes. What 2 to the power, what power will give you 64? That's 6. Okay, and the minimum number of bits needed to refer to each page that we just saw is 2. So 2 bits will give us 4 combinations, and that will help us find the page. And then within the page you'll have 16 things. You need 4 bits for that. So combine the 2 and 4 will give us 6, and 2 to the 6 is 64. Okay, so how are pages and page frames related? So we have an address space or logical memory or virtual memory, and then we'll see the physical locations of that data. So for example, page 0 of the address space goes into page frame 3. Page 1 goes into page frame 7. Page 2 goes into page frame 5, and page 3 goes into page frame 2. So the idea is that they don't have to be contiguous. They don't have to be right next to each other in physical memory. We just look at them as if they were in virtual memory. We say that everything is contiguous. Remember, that was a good thing to have. So you don't have to figure out where you are in memory. We just pretend that address space or virtual memory is contiguous, but then they really aren't in physical memory. They're all over the place. Okay, so, and notice that frames are either used or they're not used, and so the space between pages or page frames is going to be fixed. It's going to be the same size as the other pages, so they're interchangeable. So if something is not used, you can use it because every page fits in here. You don't have to worry about things being, if this unused space is being too small to fit anything in, because everything's the same size. So this solves external fragmentation. Okay, so let's take a look at the advantages of paging. It's a complicated scheme, but there are advantages, and it's what we use in just about every system that we have, like anything like Windows or Linux or Mac OS 10, they all use paging. Smartphones use it, your supercomputers use it, they all use basically the same idea. So what are the advantages? Each frame is either in use or it's not. So there's no need to compact or defragment memory. That is, we have all these teeny tiny holes spread out all through memory that we cannot use. We'd have to put them all together, coalesce them to be able to use it. You don't have to worry about that because each page frame, they're all interchangeable. So there's no more external fragmentation. We don't need to track the direction of a segment growth. When we need more space, we just use another frame. So don't have to worry about heap growing down, stack growing up, things like that. And we don't have to worry about segment growth and any of that. If you swap something out, you can swap it back in anywhere as long as you have a free slot open. Doesn't You don't have to worry about size. Okay.